All right, guys, welcome to Chapter 4. We are now moving on to something called the atom. Uh, this is basically going to be the entirety of Chapter 4, just talking about the atom, the ins and outs of it, the anatomy of it, what consists of it, all that good stuff. So, there's lots of things to cover this chapter talking about the atom itself. Now, like usual, let's always start with the actual definition of the thing we're talking about, right? The atom. The definition of an atom is that it's the smallest particle of an element that has the properties of the element. So we've obviously spent some time last chapter, chapter 3, talking specifically about elements and, I guess, kind of talked about compounds a little bit too, but kind of briefly touched on the idea of what an element is. You guys have a periodic table in front of you in your reference table. You guys also always see my reference table at the very front of my room. So you see what elements are, right? I'm sure you know a couple of different elements yourselves. But what consists of elements, in fact, are these atoms. They are these small particles that consist of an element themselves. And they essentially are the particles that give it, give that element its character, right? So if this atom has a certain number of things in it, that is what tells us it's that particular element. And I know it's very vague right now, but we're going to kind of get into it talking about some of the earlier ideas of matter, right? What's the history of this idea of what matter is, and more specifically, what's the history of this atom here? So let's talk about it, right? So early ideas about matter. First and foremost, the Greeks were one of the first people, thousands and thousands of years ago, were the first ones to really talk, much about what matter consists of, right? And the ways they kind of thought matter was consisting of was the four elements, right? Those of us who have watched Avatar, The Last Airbender, by chance, you probably are familiar with these four, right? Earth, water, air, and fire, and that's kind of what they consist of, and they weren't really wrong. They weren't super far off. Each of those four things do really and are consistent of matter, right? But more specifically, this man here named Democritus, okay, he came up with the idea of the atom itself, right? He called it a tiny indivisible particle. A tiny indivisible particle. Well, what does that idea of indivisible mean? You might have heard it actually in math class before, but it essentially means it cannot be divided, right? It's this tiny little particle that cannot be split or divided or broken down into any further than it already is. Okay, so that came from Democritus. Now, unfortunately for him, he lived around the same time as Aristotle and Aristotle's views. And if you guys know anything about the early Greek days, you know that Aristotle was pretty smart for his age, right? He's one of the famous Greek philosophers. Now, everybody kind of rallied around Aristotle and his model and his viewpoint of things, and unfortunately, not so much for Democritus. Even though Democritus is really onto something there, his idea of an atom being a tiny indivisible particle is really not wrong. It's pretty darn true. Now we're gonna fast forward a lot of years, right? A lot of years from the ancient Greek times to the early 1800s to the very first official model of the atom, and this is actually what we base our particle diagrams off of what we did last chapter with chapter 3. Um, so Dalton in the early 1800s, made the determination essentially that matter is composed of atoms, and that it's important to be able to again use this idea of models to draw atoms. And essentially, what he was able to do was he was able to essentially draw atoms as circles in particle diagrams. So you have Dalton to thank for your particle diagrams from last chapter. All right, now when it comes to atoms, especially of the same element, they have the same mass, same size, and the same properties. But the difference here is that atoms can be consistent of really any kind of element, like on the periodic table. So although you can have atoms of the same exact element having the same mass, size, and properties, you can also have different atoms of different elements that are going to have different mass, different size, and then different properties based on the fact that it is a totally different element, right? Look, so for example, if you think about the element copper, for example, the atoms that make up the element copper are not going to be the same that make up the element silver, right? Looking at silver versus copper, they're two totally different substances, right? So the atoms that make up those two things are very, very different. They're the same. They have a different mass, different size, different properties. And lastly, we've not yet gotten to this part here because subatomic particles are really important in this chapter. But Dalton's first model here, he has not yet discovered what a subatomic particle is. And this is a good segue right into our next model here, number 2, which is J.J. Thomson. and his model is called the plum pudding model. Now, he conducted what's known as the cathode ray experiment or cathode ray tube experiment. And this actually led to the very first discovery of the electron, which is one of our three subatomic particles we're going to be talking about a lot this chapter. And again, it led to this idea of what's called the plum pudding model. Now, the plum pudding model, it's kind of a funky name, right? Plum pudding. Well, the story behind this idea of J.J. Thomson's was that he did this cathode ray tube experiment, and essentially what happened was he was kind of, post-experiment, muddling in his thoughts and was eating what's called plum pudding. And plum pudding is essentially like a bread pudding that has little bits of raisins in and scattered throughout the pudding. So he essentially came, from eating this plum pudding, just basically thought to himself, "Wow, this plum pudding kind of looks like exactly what I would be picturing the elements or the electrons scattering throughout my atom here." That's essentially what this image here is in the bottom sort of middle here. It's a bunch of scattered electrons scattered throughout the atom, similar to how raisins are scattered in plum pudding. That's kind of how he came up with the idea of the model being called the plum pudding model. Now, this right here is the cathode ray experiment. Essentially, what he did was he put two positively charged metal plates, one with a positive sign and one with a negative sign on the bottom here, and he essentially shot a ray of light through and in between those two plates. Essentially, you can think of them as magnets in a way, right? Electrons that are negatively charged are going to attract the positively charged plate. So he didn't really expect anything, right? He thought this was just going to kind of shoot straight and not curve in any direction. But what happened was the negatively charged electrons attracted towards the positively charged metal plate here, which meant that this curved line here is representative of electrons that are negatively charged. And that's kind of how he came up with the idea that electrons do in fact exist. Now on to the next one here. It's called the Rutherford gold foil experiment. This is another sort of a similar experiment where instead of shooting a beam of light, this man here, Rutherford, he shot what's known as a beam of alpha particles. Now, these alpha particles were actually positively charged particles. So what he expected was he thought that this beam of positively charged alpha particles was just going to kind of shoot through this gold foil. And for the most part, he was correct, right? So if we look at this here, for the most part, he was correct, right? Most alpha particles pass through the foil with little to no deflection. But what he didn't expect was a small deflection at a very small angle like this, but also an even larger deflection over here. Alpha particles deflected at an even larger angle. And so essentially what happened was after he sort of noticed that the alpha particles were deflecting in such a wild manner, he came to the conclusion that there is this thing that is called the nucleus, right? This dense, centrally charged or positively charged nucleus in the center of an atom. And essentially, on the left-hand side here is what Rutherford expected to happen, right? He expected the alpha particles just to kind of pass through all these negatively charged electrons and have zero problems at all. But what he did not take into account was this nucleus in the dead center here, right? And that's kind of where those massive deflections came from. And again, that kind of leads to our Rutherford model. So let's quickly recap. So he fired a positively charged alpha particle at a sample of gold foil. He expected most of those particles to pass through or be slightly deflected, which again, he was pretty correct in that, right? A majority of those particles did pass through the gold foil or be slightly deflected. But what he came to find out was that a lot of the particles, although they did pass through, some of them actually deflected almost entirely in the opposite direction. And that's kind of where he came up with this idea of his model of the atom. And his conclusions were essentially that the atom is positive, or the atom is the mostly empty space with a center core of positive particles called the nucleus, right? So it's very similar to the nucleus of, let's say, a cell, for example, right? Nucleus is the center. Next up here is the Bohr model. It's the fourth one we're going to talk about. Niels Bohr is the guy's name here, and he studied the behavior specifically of electrons. And his conclusion was that electrons orbit around the nucleus in what's called energy levels, and the max of each energy level is as follows. He's got a maximum of 2 electrons in the very first energy level, a max of 8 electrons in the second energy level, and a max of 18 in the third energy level. And he also, it wasn't entirely him, but some of the people that were studying his model also kind of call this a planetary model. And this is a kind of a look at a very basic Bohr model here. Now, each of these are the first, second, and third principal energy levels that were just referred to in the previous slide here. And again, you can kind of understand why this is called the planetary model, right? You almost can think of this as like a planetarium where you've got the sun in the center and you've got all the different planets orbiting the sun. You can kind of think of this as the nucleus in the center and all the electrons orbiting the nucleus at different energy levels. We'll talk more about drawing and more about Bohr models themselves later on this chapter as well as next chapter. So we're just going to kind of segue right into the very last of our different models of the atom, which is the fifth one here, known as the wave mechanical model. This is the modern model that modern science utilizes as the true model for the atom right now. Now, it kind of gets a little obscure here in terms of how to explain the wave mechanical model, but I'll do the best I can. Basically, long story short, it's after some research in the idea of quantum chemistry and quantum physics kind of came into fruition. Basically, it's not possible to know both the location and the velocity or the speed of an electron. So as opposed to knowing exactly where an electron can be on the Bohr model, Bohr's model was kind of a little out of date because because of quantum chemistry and quantum physics, we don't actually truly know the location or the speed, right? So it's either one or the other. But because of that, scientists can predict the probable location of an electron, which are known as orbitals. Orbitals are essentially just regions in which an electron is likely to be found. Sometimes also referred to as an electron cloud. And there are 1, 2, 3, 4 SP, D, and F are the different orbitals that are kind of referred to in this wave mechanical model here. And these are the abbreviations for the different types of orbitals. When I see you guys next, we're going to talk a bit more in sort of recap about this, and then we're going to do some practice problems in class. So stay tuned, and I'll see you then.